All right, a little bit of formality, and then on to what we specifically need for right now. This term equilibrium, static equilibrium, refers to a system that is not moving or that moves at a constant speed. For right now, we'll be only dealing with situations that do not move at all. We talked about equilibrium last year. We talked about situations where if something moves at a constant speed or does not move, that the forces must balance. And so the left equals the right, and the up equals the down. The situations we'll be working with now, they can use that, but we will start with this idea instead. We'll be working with situations that have an extended object, meaning the mass is spread out and it's not a particle. And so instead of looking at just the forces on the object, we'll look at the torques. And we'll say that they must balance about any point that we choose since the system does not rotate. So take a look at these situations. We should be able to tell whether the system would rotate or whether it would or could possibly stay at rest. This first situation, the red one, this is a system that's going to rotate. If I pick any point, I should be able to sort of see that. Now, you should always pick two to make this decision. So for instance, if I choose this point, I can definitely see that the system would rotate because both of these forces would cause a clockwise rotation. But if instead I chose this point over here, I might be thinking, well, maybe things could be balanced because this force here would cause a rotation that's counterclockwise, and this force here would cause a rotation that's clockwise. And so those could be balanced. So again, you need to double check and check a couple points if you're trying to decide whether the object is definitely in equilibrium. This one here, I could pick a point like this, and I could imagine a situation where this force causes this type of rotation, a counterclockwise. This one here also causes a counterclockwise. But if this force is big enough, since it causes the opposite rotation, as long as it's big enough, a big enough torque, the system could possibly be balanced. So that's what you're really looking for, is you're looking for a situation where the clockwise torques can possibly equal the counterclockwise torques, and trying to get those straight. Other way of looking at it is to think about the torque that's the torques that are directed into the page should equal or add up with the torques that point out of the page. All right, so let's take a look at this example. We have a 50 kilogram beam supported by a wire, and we are going to first think about just the forces that are acting on this beam. So for instance, here's my pivot point, there's my hinge. I'm going to think about that there would be a force here, that's the tension force. Now, some people might be thinking, oh, isn't there a force here as well? Don't tension forces point in both directions? Yes, but I don't care what's happening to the wall. I'm interested in the beam. So we're going to stick with this first force that I drew. The other, or another force that's in this problem is the weight of the beam. Remember that the mass is all the way throughout the beam, and so the weight is pulling all the way throughout. But we can choose the midpoint, the center of mass point, and think about the weight mg pulling right there, and that's going to allow us to answer this question. Now there's also going to be forces at the hinge. We're going to talk about them, but we're also going to find out that it's not really necessary to use them in this problem because we're going to be finding the balance of torques about the hinge. That means it doesn't matter what forces are actually at that point. But the hinge would definitely exert a force either left or right, and then also a force that's either up or down. So because this force here points somewhat to the left, I'm going to have a force that points somewhat to the right. So I'll put a component force here for now. And then when I take a look at the up or down forces, I have to think about, well, what's necessary? What if I actually chose this point here as my reference point, my axis? Then the weight would cause this sort of rotation. This force wouldn't matter at all because it's acting right at my hypothetical pivot. And so my force from the hinge must point upwards in order for this to all come true. So that's really the only way that you can figure out the direction of some of those forces. Like I said, though, it's not going to matter too much in this problem because we are looking for the balance of torques about the hinge. And so the forces that the hinge actually exerts won't really matter. This force that we've been thinking through the components of does not exert a torque about point H. All right, so we're going to write a balanced equation. So the torque, the sum of the torques, must equal 0. Let's go ahead and start with the tension force. So that is a distance of 3 meters away. Actually, I'm going to write this down as well so it's clear why I'm doing what I'm doing. So I have a force of 3 meters, an R of 3 meters and an unknown force F sub t and then sine of 20 degrees. That's the angle between R and my force. And that's going to cause rotation this way. The weight is going to cause rotation the other way, so I'll consider that a negative torque. And this weight force is halfway along the beam. So I use 1.5 meters as my R. And my weight is going to be the mass times 10 newtons per kilogram, so 500 newtons. And then I don't need to worry about the angle because this is a perpendicular arrangement. All right, and when I multiply this side and divide by the numbers over here, I find that my tension force, this is the last part of the problem, comes out to be about 731 newtons.